Dave Maiulo here, and thank you so much for joining us for our Rutgers Day virtual Faraday show. Now, things are very interesting in society right now, and so many different things, so many different changes. But Mark Croft and I, are here to show you that, what was it, wiggling? Okay. Got that? No. It's going to be a problem, isn't it?
Yeah. We have to switch mics maybe.
It's okay. Mark and I are here to show you, I'm loud enough, Mark and I are here to show you that really the laws of physics don't change at all right? Even though everything else is in flux, these laws are rock solid. So without further ado, Mark Croft.
Hi. Well, welcome to the first virtual Faraday show. Hopefully the last virtual Faraday show, but we'll do whatever we have to keep it ongoing in hard times. We're going to do the laws of physics, go over the laws of physics, sort of in the order we do them in a usual lecture course. And the first of the laws of physics are that an object at rest tends to stay at rest, and later an object in motion tends to stay in motion. And here I have some objects at rest on the table, my wife's finest china, and some wonderful flowers from her garden. And I can pull them towards me if I move it slowly, and friction holds. But if I pull it very quickly, friction gives way very early, and they should remain at rest. And so here are the objects at rest, and they should not come into my face mask. Okay. So objects at rest tend to stay at rest. Now, the second part of Newton's law of inertia is objects in motion tend to stay in motion. And Aristotle, when he developed his mechanics, said to keep an object moving, you had to keep continuously pushing on it. A little bit like me resting on the couch in my house and my wife having to pushing on me to get me moving. But he didn't have a hockey puck with a fan in it that takes away the friction. And so I set the object in motion, and it stays in motion in a straight line, uniform motion. So an object in motion tends to stay in motion once it's set in motion, unless an outside force acts on it. And Dave was the outside force on the other end. So that was the first of Newton's laws. The second of Newton's laws is the F equals ma. In other words, if you push on something, it will accelerate, change its state of motion, and how much it changes its motion will depend on its mass. And here I have a very light mass object, and if I put a force on it, it should go accelerate, change its speed very quickly, and it goes flying off. The second one is a block of wood, and I'll do the same force. It doesn't go quite as far or quite as fast. And the third one is a lead brick. And the lead brick is so massive that I can beat on it. It hardly moves at all. It resists acceleration because of its high inertia. And I can even beat on my hand, and it doesn't hurt at all. Okay. The last thing I wanted to emphasize quickly is that Newton also did the theory of gravity, and a very important point in his thinking was magnetism, because Sir Humphrey Gilbert had discovered it prior to that. So if you have two objects, these are buzz magnets, quite powerful little magnets, and so if I put these guys close to each other on a table, you see that they start feeling each other before they touch each other. Action at a distance. That's the final ingredient that went into the universal law of gravitation. But we've skipped the very subtle and very beautiful third law, which is you push me, I'll push you just as hard in the opposite direction.
Not quite yet.
Oh, no, you're going to do that first? Okay, sorry. All right. Well, just tell me, give me the sign. Where were the balloons?
You know, what we have is that force is equal to mass times acceleration. Well, let's use the force
Where's the balloons?
accelerate a ping pong ball. Let's see if we can do that. So what we have here is a long tube, big plastic tube. How does that go?
All right, I need a balloon.
And pull all the air out of this really long tube. And inside this tube, right inside there is a ping pong ball. That's what I have right here, a ping pong ball. On the other side of this really long tube, I have three soda cans. Soda cans are made of metal, right? A little more solid, pretty good. Ping pong ball, light and fluffy piece of plastic. Now that we pull all the air out of this really long tube, I'm going to take a razor blade, nice and sharp. I'm going to go ahead, I'm just going to puncture the side of the tube. Now remember, force is equal to mass times acceleration. Well, the force of our atmosphere will re-enter that side of that tube. That force will then accelerate the mass of the ping pong ball. The ping pong ball gets accelerated down the tube, and when it leaves the side of the tube, that ping pong ball should be going about 700 miles an hour. But what do we have right here? We have three soda cans. What's going to happen to the soda cans? I say we do the experiment and find out, because that's exactly what we're going to have here. So let's give it a shot. 3, 2, 1. You heard that loud noise? And you know that we've had an awful lot of force on the ping pong ball. Let's see the results of our experiment. So I pop that, I pop that, I pop that. You don't know? Soda can number 1 torn completely apart. You'll also note soda can number 2 with a hole right through it. And you'll note there's soda can number 3 giving birth to a playing ping pong anytime soon, as you can tell right there. So that's force is equal to mass times acceleration. Now we do have that next law, that third law that Mark started to introduce. And Mark?
Okay. This is a very subtle law. You divide the universe into two parts, and you say if one part pushes on the other, that the other part will push back with an equal and opposite force. I may have to take off my protective gear momentarily to blow up a balloon. And here I have a balloon, and it's a two-part system. They keep making these balloons stronger and stronger every year. So now this is a two-part system. There's the balloon with the elastic force pushing in, trying to push the air out of it, and there's the air on the inside. And if I take my hand off it, the air will get pushed out of one side, and the balloon will get pushed in the other direction. They'll exert an equal and opposite force on them. Okay. Now, are you going to do this one?
Oh, let's talk about this right now. Yeah. Mark, you're going to have to stand close just so they can hear me out there, so just stay right by us. But remember that every action has an equal and opposite reaction. That's our third law. So let's take a look at that third law, because what we have right here inside this cart is this. This is a fire extinguisher filled with lots and lots of really, lots of carbon dioxide under very high pressure, lots of force. We're going to take all the force in that fire extinguisher, and we're going to go ahead and hit that sail right there with all that force. Now, when we do this experiment, my question to all of you is, what direction will this cart then go in? Well, let's think about that. Remember, all the force is going to hit here. So let's do a physics survey. Who thinks I'm going to go that way? Who thinks I'm going to go that way? Who thinks I'm going to go this way? Who thinks I'm going that way? Well, hopefully not today. But let's find out. Mark's right here. Mark, remember, this is a very loud noise.
Yes.
3, 2, 1. Which way did I go? Nowhere. In fact, the only thing that happens is your butt gets nice and cold because it'll right down your shorts. Now, why was there no motion? Well, you don't push on yourself and go into motion. That's not how this law and rule works. So now we're going to show you just how this law and rule works. What we're going to do is move our fire extinguisher over here in its cart. Mark is going to take the place of the balloon. and I'm going to stand right behind him with his sail right here. Now, I'm behind him with the sail, but before Mark goes ahead and uses the fire extinguisher on the car, here's my question to you. Do I have to be here with this shield for Mark to go forward? And the answer is no. There's no reason for me to be here now. I just want you to see the force not only on Mark, but the force that's on me when he accelerates forward. Are you ready, Mark?
I'm ready. 3, 2, 1, 0. Whoa!
Well done. Well done.
Now, when I first started doing that experiment, the first time I decided I would be the students didn't like it at first because I wasn't in danger. And so what I got was a small fire extinguisher and a pair of racing skates, and I tried it out and nothing happened. So the next time I came back with a 50-pound fire extinguisher and a new pair of racing skates, and this is the sort of phenomenon that I observed. And I need to click on here. This is me and my younger self. Yes, I have to go down here to the partially hidden button. Oh dear. Okay, I can force it to go through, I think.
Oh, we lost that, huh?
One more time. Nope, it looks like it's frozen on us. Okay, we have to hit escape.
That's it. Just move on.
Yep.
Here you go, Mark.
Yeah, hit escape on there. Okay, well, we'll have to show you that later if it comes up. Okay, that was motion in a straight line. What really happened, of course, is it propelled me in a straight line, and actually the first time I tried that experiment, I was angry that it didn't work. The second time I tried it, I got up on a 6-foot high desk, and I blew myself rotating and translating off of the desk. So I've grown older and wiser since then. Now I'm going to talk about an object that is moving in circular motion. I quite like a object on a rope, because if I push on the rope like this, nothing happens. I go like this, nothing happens. All I can really do is pull on the rope. And so when I pull on the rope, the pull is always towards the center, and I can swing it in a circle. But the force is always acting towards the center for an object moving in circular motion like this. And if I let go of it, it goes off into some direction, like a sling of old. And now...
So force is equal to mass times acceleration. Let's use that on this. What I got here? A bottle of champagne. And what we'll do is fill this glass right here. Nice glass of champagne. And now take this and put it right on here. And give it to Mark.
Yes. They'd like me to do this demonstration because I'm not too good at it. I usually end up getting wet. So what I'm going to do is swing my glass in a circle, and I should swing it fast enough that it doesn't come out, and then there we go. The only problem is I don't know how to stop. Oh, okay. I'm so pleased because now I get a drink. I needed that.
It's the first time in a while that you got that.
Yes, it is. Is his microphone, do I need to stand close to him in order to pick up? Okay.
All right, so the next one we're going to do is the lacrosse stick, Mark.
Okay. We're introducing energy then. Well, I'm an old lacrosse player with the emphasis on old. And so the point I want to make with the lacrosse stick is one of energy. If I would throw a lacrosse ball very hard at someone, it would have a lot of energy of motion, just like a pitched baseball. And if I simply put in the lacrosse stick, I can hold it well above my head and it has no energy of motion. But if I tip it and the ball falls out, it gains energy of motion when it hits the floor. So it must have had some energy already in it up here, which we call potential energy or energy of position. So high potential energy gets converted into energy of motion at the bottom, and that's one of the basic principles of physics, conservation of energy. It's also fun because the circular motion comes in. If you watch a lacrosse player and he comes down the field and somebody gets ready to hit him, he very quickly cradles the stick like this, pressing the ball into the stick so it can't get knocked out. Okay, so that's energy of motion and energy of position, and we are ready for...
You want to show the pendulum here?
Oh, yes, 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 yes. And let's see if we can we recover this screen? Let's put aside, I can put aside the, let's see if this one works. This is what I found when I first tried it. Now, I guess all the movies are, oh, there it is. When I didn't hold the fire extinguisher in the proper way, I set myself into rotation. Okay, so now here are two other systems that have energy of motion and energy of position, and I can get out a laser. And here is what we call a pendulum. And here is a real physical pendulum. If I pull it up to a certain height, just like starting with the lacrosse ball high up, it has energy of position. When it gets to the bottom of the motion, it has energy of motion. And then it gets up to another high point, and it has energy of position again. So it's constantly converting energy of motion and energy of position back and forth. I can do the same thing with the spring. There's energy in a spring. If you pull it and do like this, you can pull your chest hairs off. If you stretch it, that's energy of potential energy. And if it's not stretched, it's no potential energy. So what I can do is I can jiggle it, and you see that it naturally goes back and forth between energy of motion and energy of position in a very consistent way with a characteristic time for that interchange. Actually, I was just one little bit more. Yes. This simply shows the same thing, where the short pendulum goes fast and the long pendulum goes slow, converting energy back and forth. And then here are two springs off, a little bit off the screen, but that's okay. And one of them moves slowly and one of them moves fast, but they're converting energy back and forth between energy of position and energy of motion. Now it's time for me to put my money where my mouth is, so to speak. And here I go up to a high potential energy, which gets harder and harder the older I get. And I have a pendulum here. And if I started off here, there is a brick down there, and I have lots of potential energy up here, and I can let go of it, and it turns into energy of motion, kinetic energy, and look what happens to the brick. It turns into energy of destruction. You okay? Yeah, don't get downfield. Now, so I should be able to hold this right up to my expensive face mask and nose, not so expensive nose beneath it, which we're very thankful to the physics department for making for us overnight. and I'll hold it close to my face, and I can let go, and it won't come back and smash my teeth. Because energy has to be conserved, and as long as I didn't move my head forward, I'm going fine. I'm never quite sure if I've moved my head forward a little bit. So you can bet on conservation of energy. Fortunately, also a little bit of frictional loss gives you an extra margin of safety. Now,
And then resonance.
Okay. Remember when I stretched a spring and I just kicked it in any old way, it had a natural time to convert energy of position into energy of motion. Okay? If instead of just kicking it in any old way, I try to make it wiggle fast, basically nothing happens if I wiggle it very fast, because I'm not pulling it at close to its natural time scale for exchanging energy and position. It's resonant frequency, as we would say. If I move it very slow, it also doesn't oscillate back and forth. It all goes up and down as if it's rigid. But if I pull on it at just the right time interval, where it likes to vibrate, the motion builds up and up and up and up, and basically it shakes itself apart. And that's the phenomenon of resonance. And now Dave is going to do, I do the simple, dangerous experiments. Dave does the one that takes real skill, and now he's going to do a very, very nice experiment.
I hope that's true, Mark. But what we have right inside this box is a beaker. You can see it right there. And that's actually on camera right up there, too. And I can resonate that beaker, but instead of touching it, physically touching it and resonating it, I'm resonating it with sound. I'm shaking that beaker with sound. So that's exactly what we have there. So now what we can do, well, let's see if we can actually see it shake. So I'm going to turn this light off, and I'm going to turn that light on, and now turn off some of these lights. But now give it, once again, that sound. We should be able to see, and you can see right there, right at the bottom there, there's a shaking now to the edge of the beaker. We're right at that resonant frequency of the beaker. So now let's give it too much energy. And in giving it too much energy, we should go beyond the physical ability of the beaker. Let's see. Looks like it's a little bit off. Try one more time. Oh, that might be better. Sometimes they make tough beakers. You just never know when they're going to break it. So wait, what can you do? Put them back together? That's not going to happen. So
if you look at some of our other shows, all the other beakers broke.
It's all right.
Okay. All right, so what are we up to?
So right after resonance, we want to do the wave propagation. Right?
Okay.
So we got our rope slinky right here. You guys want to start to just take those things off there? That's great. Leave the camera, of course. And what I have right here, oh, let's turn this rope off. Okay. So what we have right here is a nice long rope slinky. Mark's got one side. I have the other side of this really long rope slinky. We're going to hold this up a little bit like this, Mark. Really loud. Okay, good. So what we're going to do now is we're going to go ahead and give this rope slinky a karate chop, a wave pulse. And in doing this, you can see that pulse propagate across that spring. It really kind of moves in a nice physical way across it. You see the karate chop as it moves across that spring. Louder. Okay, good. So let's try that right now with this. So wave propagation, well, we want to do wave propagation with this. Now, what's this? Well, this is a garbage can, and it's got a hole in the bottom of it, and it's got a rubber sheet right here. What I'm now going to do is show you that you don't really see anything happen as I hit this, okay? There's nothing happening to our screen. You don't see anything there at all. So you really don't know anything is happening. But in science, sometimes what we do is we see the effect one thing has on another. And that tells us an awful lot about what's going on. So I'm going to light this candle right there. And now I'm going to take this device, and I'm going to be able to, oh, you don't have to hold it, Mark. It's okay.
Oh.
But they can see the candle, and they can see that I can now use this to blow the candle out. So you see that something is actually going on when I use this device. But you still didn't see exactly what's happening when I hit here. And you know what? In science, what we like to do more than anything else is see exactly what's going on. So let's give it a shot. To do that, we're going to put a little theatrical fog in our garbage can. Now, theatrical fog, no problem. It's really not, it's pretty innocuous. But now we can actually see exactly what's going on when I hit the bottom of this garbage can. And isn't that pretty? Boy, I had two destruct each other. Right towards you at home. Those beautiful smoke rings. And this is a lot of fun. And if you're home and you're bored, hey, get the pieces to this, rubber sheet, duct tape, garbage can. You can even make them out of a 55-gallon drum. And goodness knows we have a little bit of time right now. Now, that's our garbage can with the circle. What's that shape? That's a circle. What's this shape right here? That's a square. So let's take the square and put it right here on the front of our garbage can. We have a square then. You here at home, what are we going to see now? What will we see come from this garbage can? Well, I say we do the experiment and find out. That's the only way you really learn in life, is to do the experiment. So let's go ahead and do that. A little more fog in here. And now, what do you think we're going to see? You tell yourself at home, what are we going to see? Well, what we're going to see is smoke rings. They're really, the only really stable shape that comes from this is that smoke ring right there, as you can tell. You know, smoke squares are like unicorns. You want them to be real, but they do not exist. Okay, that's the way it goes. So that's what we have from our garbage. And now, what we did, we were in our lab, and we were playing. And actually, that's what scientists like to do more than anything else, is they like to play. So the shape we're going to use now, thank you, Mark, is an ellipse. I'm going to take this ellipse, I'm going to put it right here on the front of our garbage can. We just kind of were playing, so we just kind of did this by accident just to see what would happen. But it turns out that with the ellipse on it, we can actually see this, a back and forth ellipse, a quadrupole motion. And this is exactly what we get when we're looking at those gravitational waves propagate through space. They propagate through space in almost a very similar way in that quadrupole that we're getting there. So here we are doing cosmic physics, you know, really, really cosmic physics with a garbage can. That's what you can do when you do some science, all right? And Mark, I think, has something to show you there too.
Yes. HTML. Oh, there we go. This is an actual simulation of the vibrational waves that they pick up from the merging of black holes, that they pick up of gravitational waves propagating through the space. And you see it's an ellipse that's fluctuating back and forth with the long axis one way and the long axis the other way, a quadrupole oscillation like Dave's mentioned.
You have your simulation ready?
Okay, we're doing standing waves. Okay, they have disappeared temporarily. Oh no, they're up there. Yes. Okay, let me tap on, there's that one. And then down here is this one. And I have to move this guy down so you can see both at the same time. You can have waves that propagate through a medium or along a string, and you can see there's two examples right here. Here is a wave that repeats in space, and you see the repeat distance in space is very small, which means it has a short wavelength. And you can also see it's generated by a rapid, high frequency vibrating up and down. So this is a high frequency wave with a short wavelength. Here I have a low vibrational time period, a very low frequency, but a very long wavelength. The distance between maximums actually goes out the window here. Okay? So these are the two types of traveling waves on a string. Now the example of interference going in both directions I may or may not have. Let me see.
That's okay, Mark. We can just go right to this.
Okay, we can go right to the example of that.
So what I have here is a wave pulse. I'm going to just flip the string, kind of like a guitar string, and you can see that pulse, just like our rope slinky, moves back and forth across there. But if we do this in just the right manner, the nice consistent manner, continually giving it a pulse over and over again, you create that standing wave. And Mark, why don't you take over?
Okay, at very low frequency, you have the longest wavelength wave because it has to be a zero on both ends, and it has one maximum in the middle, zero on both ends. Now you increase the frequency, and you get the next higher standing wave. Okay, a zero in the middle, zero on the ends, and two maximums here and here. Okay, and then the next higher frequency. Now you see two zeros here, a maximum in the middle, a maximum over here. We're in and out. It's shaking the end a little bit.
There you go.
Lower amplitude. Okay, so this is three maximums. This is very much like a guitar string where you would put your thumb in order to make a certain tone. And do we want to go any higher?
Try it.
Whoa.
Not quite stable.
There we, oh!
There you go.
It's a little unstable. Okay, so those are standing waves on a string.
Now, you know, what travels as a wave? Well, what travels as a wave is sound. Sound, right? Sound is a wave. So here's what my question is for everybody there at home. Let's do that. Let's do that. Boy, oh boy, oh boy. It's one of those things. It's just Murphy raising his ugly head constantly here. It is not going.
Oh, stop the screen mirroring.
Oh, that would do it, yeah. Oh, thank you. Beneath is a man on the spot. Here's my question to all of you is, how large is that sound? And I bet you can hear it, right? Probably better than you can hear me. But how large is that sound? Well, we don't know, right? We can't see sound, right? We can see an elephant. We know an elephant is really large with our eyes. We know it's large. You know a mouse is really small, but you don't see sound. We hear sound. We know sound is either loud, soft. We don't know if sound is big or small. But here in our show, we can show you just how big that sound is. Now, how are we going to do that? We're going to use fire. And you probably knew that already. Just like that. Right across, and we'll turn it down to a nice even flame. And now go ahead
Hit the lights, huh?
and put that sound back inside. Because now we can see the size of that sound. That's how large that sound is. That's That's our sound wave in the tube, but visualized by the flames in our tube. So there it is. But what if I go higher in frequency, higher in pitch? What happens to the size of the wave? Well, how do you learn in life? You do the experiment. So let's do the experiment. Let's go ahead and change the sound. Higher pitch, but smaller wave. And we can go lower. We go lower. It's actually a bigger wave, as you can see. That's just one sound we're using all this time. What if we put a song in here instead? What if we went ahead and put a song in our tube? What would we see then? We'd see a lot of the dancing waves in a song. And I bet you've probably, if you've ever been to a wedding in your life, you've probably heard this song yourself. I'd love to give it a little more gas. And let me see if you know this one. And there you go. The dancing waves in a song. And this shows you that song is made of lots of different waves. And you can kind of visualize the song in the flames of our Rubens tube right here. I hope you enjoyed that one. It is one of my favorites of all time. Here you go. All right.
I'll hit the lights. Okay, where are we up to?
We are up to, we got our balloons, right? Got our balloons coming?
Oh,
Now
density.
sound is a wave, and that wave is sometimes affected by the density of the fluid that we use. So now we want to actually have, there we go. There you go. This one's for me. Okay, and that one's for Mark. And I have a feeling, don't turn it off. Don't turn it off. Don't.
Okay.
I have a feeling you've probably in the past listened to somebody who's breathed in some helium. And when they do that, what happens to their voice? Well, I bet you know that already too. They sound a little like Mickey Mouse, so here we have Mickey Mouse.
I'm the comic relief here, you realize.
All I can say is there must be a more reasonable thing for me to do. More dignified.
But here we have a gas that's more dense. All right? So let me breathe this, and let's see what happens to my voice at that point.
And I think you can tell immediately my voice is not a lot deeper. Look, I am your father. That's right, it's the Darth Vader gas I have in my hand right now. And it is rather dramatic, and it takes a little while for this to leave your lungs. The helium leaves your lungs pretty quick. It wants to get out of there.
Well, I still talk like Mickey Mouse. No, I don't. I thought it was.
There you go. Salt hexafluoride, helium. Yeah, that's what we got to do. There you go. So you're now on here?
I hope I am. Yes. Are we on?
Your computer, right?
Yes. We're starting gases.
Yeah.
Okay. So let me. There we go. I've got to get the mouse in the right spot. Now I want you to learn something that is quite simple, but is quite important. Remember, we talked about energy before. Energy of position, energy of motion. If you have a gas near the surface of the Earth, it's comprised of molecules or atoms, and they run around. And if you have, say, a high temperature on that gas, you will notice that the molecules or atoms are running around very fast. So that means they have a high energy of motion. Some move slow, some move fast, but it's the average energy that gives.
Right? I think it's light first. Don't you want to get the iPad on the screen? I think it's light first, then we do that.
Okay. Well, I'm almost done, actually.
Yeah, I know.
Want me to kill it off?
Yeah, why don't you, because we have to go back to that when we have the drum here.
Okay. Well, you can forget what I've just said, or you can remember it, and you'll be ahead of the... Got to go with the boss here. Okay.
So your block?
Okay. Now, we were talking about waves, and now let's look at another type of wave, and that is electromagnetic radiation. And a very good example of that you can find in a laser or any sort of light. And here I have a block of material that I actually dove into a dumpster to find. And you can see the track of the laser beam as it goes through the block of material. You see some reflection off the top surface, but then I want you to notice the laser pathway coming in bends when it goes into the more dense medium. That's because inside the block, the speed of light slows down because it's in a material. It has to vibrate the electrons. And you can also come around here, and if you come around this side and you shoot upward, you see that you get reflection off this surface, but nothing comes out the top here. You'll notice that this is what we call total internal reflection. Okay, so the light always stays inside the medium, and that's what they use for optical cables in order to transmit information. Now, that laser is a green laser, and one has to handle lasers very carefully. Here's the violet one over here. You have the screen?
Yeah, let me, got right there for you.
Okay. Here we have a fluorescent screen that if you shine the green laser on, well, it reflects off it very nicely. But if you take a violet laser, it has a higher frequency and therefore a higher energy, and it can tickle the atoms of the material in such a way that you can actually draw on it. This is a phosphorescent material. Put little horns on him. That's Dave. Okay, so the violet is a higher energy light. Oh, yes. Why don't you hold it up with the circle not near your face? The opposite way. There you go, up high. Yes. You have to be very careful, and you notice that this is a glow-in-the-dark toilet seat, which as you get older, you appreciate more and more. Okay, so the violet light makes it glow. Okay, you'll notice that we tried to be very careful with lasers. You shouldn't pick up a laser and play with one unless you have somebody that's a real expert around, because they can often be quite dangerous for the eyes. This block of material that I say I dumpster dove for, I want to emphasize another point about. It was chosen so it would fluoresce when high energy particles came through it. So if you use violet light on it, you see it glows very nicely. And here's another violet light. And violet light you have to be particularly careful of, because that's also more dangerous for the eyes than most things, than other longer wavelengths of light. And so you see it glows. I don't think I have the hairspray for my hair right now, so we'll skip that. Okay, so you're going to switch to
the iPad right here.
Now this is a real innovation. That Dave and the guys have, and his students have developed recently. We used to give out at the Faraday lectures the diffraction grating goggles, which separate light into its various colors. And this, are we doing this guy, or this is a fluorescent light? This is incandescent. Oh, it's a regular light bulb, incandescent. Okay, so you can see here's the light bulb in the center, but when it comes through the diffraction grating, which is a bunch of rulings on a piece of plastic, or it could be on glass, but this one's on plastic, it separates it out into the colors that are in the in the white light here at the center. Oh, so it goes, there's a Roy G. Biv. Roy G. Biv means it goes from the red, orange, yellow, blue, indigo, violet, or if you like history, Richard of York gave battle in vain. This spectrum right here tells you the temperature of the element inside here. So Dave's going to change the temperature. It's getting cooler now and less bright. And I want you to notice that it's disappearing from the blue side first. So the high energy light is oh, that's beautiful right there. The blue's all gone and now it's just green and red. Okay? So it's at a much lower temperature. If you were a blacksmith, you knew this because you didn't start beating on a piece of steel iron until it was white hot, because you knew it wouldn't bend until it got hot enough. And you want to turn it down even further? Wow, that's beautiful. This is one of the best examples of this I've seen. We've just developed this. Dave and his crew have just developed it. Now you can see it's almost all red. And then you can keep on going, and it goes into the infrared. Oh, you're coming back up? Okay, he's turning the temperature back up. And you can see various stars in the skies, and they're different colors by virtue of the fact that the temperature of the surface of the stars are different. Okay, which one are we on next?
Now, what we should probably do is show them how this diffraction grating works. So I'm going to use this guy right here.
Now, do you want to talk about this? You want me to stand over by you?
Well, what we just wanted, why don't you just point out that we have the different colored lights on that one source right here, and we can see that basically the diffraction grating works. It spreads light out in a different way. You know, what we do in physics is we dissect light. We don't dissect animals. That's way too messy. But we dissect light. So we can see exactly the pieces of light that are in any light source using these diffraction gratings.
And these are light-emitting diodes, right?
These are light-emitting diodes. Yes.
Okay.
So you can see that the one at top, which is all white, that has that whole spectra. And then you can see we go from red all the way to purple. And you can see how it spreads out in a different way. That's what we have with that light source there. But now we're going to go to your favorite. Well, not your favorite, but we're going to go to hydrogen.
Well, how could it not be my favorite? I teach astronomy these days, and this is hydrogen. There's some reflections that go on here, but what I want you to look at is these sharp lines right here. In particular, I want you to look at this red line right here. It's a symmetrical pattern on both sides. This is the most famous light color in the entire universe. It is the transition from one electron dropping between the first two levels of hydrogen and giving off, no, it's not the first two levels, it's the third to the second. But at any rate, this is the red Balmer line. Hydrogen makes up 80% of the universe, and it's a way that you can characterize stars. And here are the other lines. And when they saw this in the 1800s, they didn't understand at all what was going on, how you could create sharp individual colors from a glowing gas cloud. And now we're going over to
Helium, yeah.
Okay, helium.
Thank you, Michelle.
Now this is helium. I said that 80% of the universe was hydrogen, the other 20% is helium, and everything else is just the leftovers. A beautiful spectrum, guys, beautiful. And look at this beautiful yellow line. Remember, our sun looks pretty yellow. That's because of its black body radiation temperature, but this yellow line, in fact, was never actually seen until an eclipse came around and they looked at the gas above the sun in the coronosphere. And they saw this glowing yellow line that they'd never seen on Earth before. They had seen spectra for almost all the other elements of the periodic table, but they'd never seen this before, so they named it helium after Helos for the sun. It was the only element of the periodic table not discovered on the face of the Earth. Okay.
Next one here. There you go. You know
Hydrogen.
which one that one is, Mark?
Is that Mercury?
That's Mercury.
Okay. This is the mercury inside a fluorescent light bulb. And they use mercury on the inside of the fluorescent light bulbs, which means disposal of them, you have to be very careful.
I have one of those right here.
Yes, yes. There's some other elements that they mix in with the mercury, but you can see the main lines here are the mercury lines, okay? And this is just a common fluorescent light bulb that you can buy at the store. They've got some admixtures of some other materials in there.
That one down, we'll go back to our last one right here. Oops, there we go.
Yes, this is the neon. This is the cowboy one, right? The neon, and you can see it has lots of beautiful spectral lines here. Some of them are very close and are split, and each atom of the periodic table has its own, we call this spectroscopy or spectral signature. It's a fingerprint of the wavelength that glowing material emits when it's heated up in gas form.
But not only do we have the glow of each one of these individual atoms, but we can also see with this same thing, here's our regular light source once again. There you go. But what we're going to do now is turn on a bulb above it. And you can see that there's a difference between the two spectras that we have coming from those two different bulbs. Even though they're identical in every other way, the top bulb has a screening material on the top which absorbs the yellow. Thank you, Mark, for pointing that out. So it absorbs that yellow, and that actually shows that material picks up that yellow, it keeps it in there, so it doesn't reach us. Well, when we look at these gas clouds in outer space, and they have lines in them absorbing the light that's coming towards us, we know exactly the material that's in that gas cloud using this very same method. So this is absorption now that we have here, not emission.
By the way, every single star, when we look at it, we see these absorption lines and we see the elements in the atmosphere above the star. And that's how we actually classify stars also.
Now, let's see how much fun we can have with this, because I'm going to turn that one off, and that one off, and this one off. And as our lights basically shift through the different colors, you can see that color mixing in action. This is the lights, that strip of LED lights changes. You can then see those colors pop. Isn't it fun this way?
Yes, it is. This is a beautiful job. We've always in the past had to have people in the audience with the goggles on them.
Wonderful. Well, we did a good job with this. So now we're going to move on to infrared light. And for this, I'm going to go ahead and put this on and turn on some lights.
Let me go to HDMI 2.
All right.
No, HDMI 1. Yes. And let me kill some things in the front. You go ahead, Dave.
All right. Well, what I have right here is a clear camera. I have to show this, though.
Yeah, yep.
And, all right. Oh, wrong one. There we go. All right.
Where's my bag?
And this basically shows that infrared spectra. Oh, first let's do the shield. That infrared spectra we have, in fact, what we're going to do is show our camera person, Joseph. Joseph is waving. He's a good man behind the camera. But we can see that Joseph is emitting that different light because he's warmer than the rest of his surrounding area. So he's just like that. And just like that, I can put this on Mark. We can see that Mark is warmer too. But Mark has a shield here, and he's going to put that in front of his face.
Well, it's already.
Yeah, and you can see that the plastic absorbs that infrared. It doesn't get to the camera. It's blocked by glass or plastic. We can see with Mark's shield on his face.
Here,
also
I can temporarily take it off. I'm a disembodied head now. Okay. So now we want to do the bag.
Now we'll do the bag. And Mark also has a garbage bag. And what Mark is now going to do is take that garbage bag and put it over his body. But I want you to see that really we can still see Mark with the infrared camera. You can see how effective this is. The infrared signal goes, that light goes right through the black plastic. Visible light does not. We can't see Mark with the camera we have.
Can you see what I'm doing?
With this camera, we can see right through. And he's sticking out his tongue because he's that kind of guy. There you go. There you go. All right. You want to find now your pictures from the...
Yes, they're hidden behind...
Did you find those?
Okay, let me just see if I can... Ah, yes. Multiple screens. We've talked about these waves. I can just kill those. And let me... Ah, yes. This is what happens when you have multiple screens on the same computer and you can't find one for the other. Okay. That's the one I want there. And now I have to go over here and there we go. There were the standing waves that we showed you, the first three standing waves. And we showed you the bending of light. And, oh, this is the part that I wanted to show to you. We did nice spectroscopy, but if you look out in the sky, especially at wintertime, you will see the constellation Orion, and you'll see the big red star Betelgeuse, and its spectrum is mostly in the red. That's why he looks red up in the corner. He's a red giant. And then the belt stars and Rigel down here are white hot stars, and so they're mostly into the blue and not much into the red. Then there's the brightest star in the sky here, Sirius. But if you look right here in the sword, there's a glowing red cloud of hydrogen. And remember that red line for the hydrogen? Well, we see that famous red line, the bomber line for hydrogen in the Orion Nebula.
So now we're going to do the...
Okay, and I'll go back to the computer. Oh, no, that's in HDMI 1. And I have to get this guy off screen. Okay. Now let's go back to temperature. And I suppose I should put on my face mask again. And,
Well, let's do the balloons first.
okay, which ones?
These guys...
Huh? Oh, you mean do density first?
Yeah.
Okay.
So what floats in air? Well, it's about density, isn't it? We all know that helium balloons float in our regular air that we're used to. Our regular air is mostly nitrogen, all right? So these balloons float very well in the nitrogen, right? That's less dense. That helium balloon that's less dense. And Mark here, he's got a stick with some matches, and he's got a lighter, and he's going to show you what happens when we light those particular balloons up.
So this is a helium balloon, so it should just go pop. You guys haven't mixed up the balloons, have you? Sometimes I mix them up just to shake me up. No. Well, you see it blew out the candles also, or the light, the matches. This guy is not helium. It is a lighter element, hydrogen, and when you light it, it burns with oxygen to form H2O or water, and so if you were actually sitting here, you would feel a flash and a concussion of pressure. So let's give it a try. Yeah. Yes, and you notice it didn't blow the matches out because it was too busy burning itself. It didn't rob them of oxygen.
Michelle, do you think you have it? Yeah. Okay, let's see if we can see that. I think it's slow motion.
Yeah, I'm scared.
There you go. Quite dramatic. Quite dramatic.
Thank you for the slow motion. These guys have really gotten much more sophisticated.
Now, what were those balloons floating? They were floating in that area. Now, Mark, you can go back to your simulation over there.
Okay.
I'm going to turn this on. What I'm going to do is pull all the air out of this really large drum, all of that air. And what happens is when the air that's inside the drum goes away, well, really, there's nothing then on the inside of the drum. Oops. Come on in. There we go. There's nothing then on the inside of the drum like holding out that air pressure from the inside. So sooner or later, this drum will then implode. And Mark?
In the meantime, don't even think about this, right? Just forget it's here. It's slowly pumping the air out. When I was talking earlier, I talked about the air consisting of molecules and that the temperature of the air was proportional to the average energy of motion of the particles in the gas. So that means this is a hot gas, so I think it's about 9. Well, it's not ready yet, but you get an idea of what we're waiting for. This is a very low temperature gas, and you see in this low temperature gas, the molecules are moving slow. So don't let anybody try and tell you any complicated thing about temperature. Temperature is just a measure of how fast the energy of motion of the particles in the gas are moving. So it's just like a ball's flying around. If they're flying around fast, it's high temperature. Notice that when these guys hit the wall, they bounce off, so they push on the wall hard. Here, when they hit the wall here, they bounce off very softly, so there's almost no push on the wall, and therefore the pressure is low. And here the pressure is quite high. Now, if I turn up the temperature on this lower one down here, and let me see if I can find my cursor. There it is. Yep. Let's add some heat. If you add enough heat, you'll end up pushing on the walls, and you notice this has a lid on it. And if you turn it up enough, you can blow the lid off because of the gas molecules moving very quickly. Now, up here on the top, I want you to notice that I have no gravity on. Suppose I turn on a lot of gravity. Okay, let's put a lot of gravity on here. Temperature goes up, but that's not the most important thing. I want you to notice that the particles up here very high are going slow. The ones down here are going fast. And the number up here are very few. But you know this is true because you've seen mountains and mountain climbers, and you may have climbed mountains yourself, and you know it's cold at the top of the mountains. You know it's hot deep down in Death Valley at the bottom of the mountains. And you know that the pressure is small up here, and the pressure is large down here. So this guy's still pumping, huh?
He's still pumping.
Okay, well, we'll just continue ignoring him. Let me see. What can I start on to next?
Well, we can go ahead and show them what we're going to do here, Mark.
Okay.
We have a pressure experiment just like the one that Mark showed us with the simulation. And what I have here is some very warm water in a garbage can. And what we're now going to do, and if Vinith pulls this up, here's our experiment. Soda bottle, LN2 in soda bottle, warm water in garbage can, then LN2 bottle in warm water, and then ping pong balls on top. And just like that simulation, when it basically blows the lid, we should see just how dramatic this is. So let's see if we can see just how dramatic this is. You ready with your ping pong balls beneath? Mark, you're going to have to move away.
Okay. Will I get my feet wet? Oh, that was...
Well, that was pretty good time.
Okay. And here you can see what's happened to our 55-gallon steel drum. Remember that what was happening here was that the hot gas molecules were high pressure gas was hitting on the outside, but we pumped all the gas out of the inside, so there was nothing pushing out to balance it. So it came down to the strength of the drum, which we exceeded eventually.
Now, Mark has his table right here. So
Okay.
all for you, Mark.
Okay. Now, this is liquid nitrogen I'm going to be dealing with here. And there's one word of warning that I want to say, or a few words. Liquid nitrogen is potentially extremely dangerous. It's 77 degrees Kelvin. It will freeze things very, very rapidly. For instance, right here, we have a few objects that were in there. Here is, for instance, a hot dog. I've done this very quickly. I've been handling these liquid nitrogen since, I believe, about 1966. Okay, so it's been a long time. If I hit these hot dogs with a hammer, they're very brittle and they smash. And that's what will happen if you stick your finger in liquid nitrogen or you stay in contact with it too long. Maybe I'll put a glove on. I usually can orchestrate it so I'm in contact with it for an extremely short period of time. Here are two more objects. I'll save this one gently. And I'll put this one up here. And this is broccoli. Now, I used to not be a fan of broccoli, but let me tell you, if you put some garlic on broccoli with olive oil, it's absolutely delicious. But for those of you who haven't learned about that way of preparing broccoli yet, let me just smash it. Okay, so that was a broccoli explosion or crushing. And now here is a banana. Now you all know what a banana is. And so that's a banana. And similarly, it's very hard because it's very cold. So when I hit it, what do I get? A banana split, right? Okay, well, physics humor may not be all that funny. Now we come to my favorite demonstration. Oh, let me do one more of these. I'll do the other one later. Here are some nice soft flowers. And if I stick them in liquid nitrogen, they become as brittle as glass. And that if I then, let them keep cooking right here. Okay, that should be enough. They become so brittle, they smash like glass flowers. Okay, so liquid nitrogen can freeze things very efficiently to a very cold temperature. But this last demonstration, it's not the last of these, but this demonstration right here is the one that's my particular favorite. I see I've used the wrong thing for it, but that's all right. This is a helium balloon. And if I let go of it, it's less dense than the air, so it will float up to the ceiling. If the ceiling wasn't there, it would keep on going. So now I'm going to start cooling the helium. And when I start cooling the helium, that means the molecules or the atoms of helium move less fast, less energy of motion, lower temperature. They hit the walls less hard. The balloon starts to shrink, and the balloon plus helium becomes more and more dense. And as it gets more and more dense, eventually it gets to the point that it's more dense than the air, and the helium balloon no longer floats. Can you see it okay? Do I need it over a little bit? Okay, did you see it okay? Okay, good. All right, so it then floats. So that was just the demonstration that I showed you to with the simulation earlier, in which you could cool it down and heat it back up. This last one here is one of my favorites.
Remember, right at him.
Okay, right at? Okay. This is called the liquid nitrogen cannon. So if I put liquid nitrogen in here, it boils vigorously. And if I cork it, it will develop high pressure, a little bit like a cannon. And so let me, whoa, I don't think we want to shoot it right at him.
Yeah. He's brave.
What if I get the camera?
You got a leak.
I got a leak. I got another leak.
I see another one.
Okay, try one more. I got my thumb caught in there. These gloves.
That's a bum port.
I'm putting it in too hard. Oh, the heck with it.
Why don't you move on over there?
Okay. You saw it. The reason I like that demonstration is my father used to work in a nitroglycerin factory. And when he got hired, they put him in a laboratory. And it had 3 very strong walls and a very weak wall. And he asked, what's that for? They said, oh, that's a blowout wall. If you make a mistake, there's an explosion, it blows out the wall, and then we hire somebody new, sweep up all the glass, and we can continue on. But if you are going to work with explosives, you want to have something like a blowout wall available. Okay, now 2 things I would like to switch this back to the other computer. And
You don't have a lot of time. So.
okay. All right, so let's get to the physics at first. The most important thing I want you to realize here is this is a magnet. And what this is an old-time oscilloscope, which for our cases is just an electron gun. It shoots charged particles at the front screen. And if I put this so that the charged particles run right down the magnetic field lines on the end of the magnet, you can see that the dot stays at approximately the same spot. We're able to follow that all the way in and out? Okay? All right, now, we also have a hole here. You don't want to have an open old oscilloscope because there's very high voltages associated with it. But we have a hole in just the right spot where we won't get electrocuted. Probably won't get electrocuted. No, we won't get electrocuted. And we try to shoot the charged particles across the magnetic field lines. So if I put it in here like this, and I can't actually see it gets deflected to the side. If I reverse the direction of the magnetic field, it gets deflected to the other side. Okay? So charged particles, when they try to cross magnetic field lines, get deflected to the side. This is the reason that we are protected from the charged particles streaming at us in the solar wind from the sun, because they hit the Earth's magnetic field and they get steered to the side, but then they come straight down the magnetic field lines near the poles, giving us the aurora borealis and the aurora australis, the northern lights and the southern lights. Now the next thing is, what's the interaction of a magnetic field with potentially moving charged particles? And can you see a galvanometer okay? Okay. Oh, that's actually here. Yeah. He could have done it up there, I think, too. Here I have a coil. Yeah, so you want to show the coil. And here I have a magnet, of course. And the thing to notice is that in this coil, if I change the magnetic field inside the coil, I get electricity flowing in that galvanometer. Electricity goes one way, or I pull it out, it goes the other way. I put in the other direction and the out. So a changing magnetic field in a coil of metal will make electricity flow, and if you put a rotating magnet inside of a coil like this, you can generate alternating electricity very much like you do with it at a hydroelectric dam. Okay, so that's the Faraday effect. Which one are we on?
Use your eddy current tube.
Eddy current tube, okay. Yes. Now, you guys realize that the real expert here is Dave. And he would be doing 90% of the talking if it wasn't for the fact that his mic isn't working. So I apologize for giving you a second string guy, but I'll do the best I can. Well, that's the fact of the matter. This is a long copper tube. Did you get a shot of the entire thing? Okay. And then up here on the screen is looking down the barrel of the tube. This tube is actually a piece of copper wire that carried so much electricity that you had to cool it from the inside through water flowing through the hole. But if I drop a magnet through it, the tube at various heights sees a changing magnetic field. Electrical current flows in a circle in the tube, and the thing floats down very, very slowly. And I'll catch it so it doesn't bounce. And this, by the way, was given to us by Tim Koth. It comes from Fermi Laboratory. And so that's a very nice example of induced currents in a material in a changing magnetic field. And I have to wait for it to drop all the way through. Okay. Okay, so where are we up to?
This guy's good for you now?
Okay. This is the same thing, except instead of dropping the magnet, we send a metal in between. Thanks a lot, Dave. Here I have a solid piece of aluminum. Here I have a magnet. Aluminum is not magnetic. But if I try to roll this through the magnet, it will see a changing magnetic field and electricity will flow in a circle. So the energy of motion gets converted into electrical energy. Okay, so we lose the energy. Here is another object that is all cut up in the middle. Lots of big holes have been milled out, but there is a contiguous path around the entire rim of this piece of metal so that there's still circular motion of electrical current, and you see it shows the same effect of slowing down when it hits the magnet. Now finally, I have to illustrate to you that it really is electricity flowing in a circle. So here I have an object that is basically a solid piece of aluminum just like the others, but it's cut alternately from one side and then the other side and then the other side. And so the zigzag pattern doesn't allow electricity to flow in a circle, and so it goes through the magnet as if it's not there. No circular flow of electricity. Now, Dave has very nicely already prepared here a liquid nitrogen cooled disk, and the amount of the electricity that will be induced flowing depends on how much the material resists the flow of current, and that drops with temperature. And so now we get the effect, it's so big it actually freezes. Okay, there we go. There was a slight kink. See how slowly it goes through, because the resistivity is less and you get more electrical current. Okay, so that's the inclined plane with the Faraday discs.
You only have time for the ring flinger too.
Okay, ring flinger it is. This is another illustration of the same concept. Here we send electricity around in a circle and it creates a magnetic field. But it's alternating current, so when the electricity goes this way, the magnetic field points up, and when it goes this way, the magnetic field points down. So there's a constant changing magnetic field in this thing that we call the ring flinger, for obvious reasons. For reasons that will become obvious in a second, I can do this one. Here I have a ring, and I put it on here, and I turn on the changing magnetic field, and it shoots it up. I used to have a kid come up or a child come up, and I'd say put this on here like this, and then I'd turn on the electricity and play a little trick, and the child would go like this, you know, and try it a couple times, and it wouldn't work, and then I'd turn it off and say, no, put it on like this. I've stopped doing that on the advice of my lawyer, or at least my friends. Then here I have a solid disk that shows the same effect, and the reason I do that is because here I have a slotted disk where nothing can flow in a circle. And so when I put this guy on here and this guy on here, Thanks. The one that's solid jumps, and the one that's not solid doesn't. Okay, I always have to do 2 at a time because the children wouldn't trust me after the previous stunts that I pulled. Oh yes, and the last one is I have to show you that what's really happening is the flow of electricity, and here I have a coil of wire with a light bulb, and so if I turn this guy on, the changing magnetic field induces currents, and I light a light bulb with the current that's created in the copper wire due to the changing direction of the magnetic field. Okay, so we're up to...
We've got a reward for all of Mark's very hard work. What we have right here, Mark, is the bed of nails. No, not yet, Denise. Just let me show this to the camera. And I'm going to show you that these nails are actually really sharp.
That's a variation of Newton's law draw.
That's exactly right. It's all about that apple, right? So here is that apple. You can see the holes that those nails put in the apple. They're very sharp, actually. Now, beneath, a little help, because there's about 3,500 nails in each one of these beds of nails. We're going to lay this one down here. Mark will then put his body right across that bed of nails. You ready, Mark?
Yeah, it took a long time to work this demonstration out. We went through several professors along the way. I had the toughest skin of them all, I think.
Oh, very good. A second bed of nails.
Oh,
Right down here on top of Mark's student worker, Michelle. And was she ever in your class, Mark?
I don't remember.
Oh, I don't know. So
Oh, good.
But you can get right up on top. So you can see that now. Michelle on the bed of nails, on Mark, on another bed of nails. Fantastic, Michelle. Come on down.
I think
Now move that.
Dave usually refers to that as a bologna sandwich.
So why don't we do this? Why don't you stay right there? Why don't we do this? Well, it's not magic, it's physics. So right here, I have something really similar to Mark. Thin skin and filled with hot air. Wow, okay, you
Oh.
can see. That's our
Can he hear okay?
here. So, what can I do with this balloon? Well, let's pretend that my bed of nails, I weigh 200 pounds, 200 pounds. My bed of nails has only one nail. Well, how many pounds of force on that one nail? 200 pounds of force. More than enough to drive that nail right through my body and kill me. Here we have, let's say, 10 nails on a bed of nails. Well, that would be 20 pounds on each nail. More than enough to drive those nails right through my body and kill me. Let's say my bed of nails had 100 nails. 2 pounds on each nail. And you actually need about 12 pounds of force on a nail to go through human skin. So you need less nails to actually hurt you, more nails that you don't have enough force. Let's take a look at that, because again, our friend Mark, a whole lot of nails, and it doesn't bust, that balloon doesn't bust on all those nails. Here you have less, half as many, doubling the force. Doesn't break there either. But here, even less. Not many nails, much more force, and your balloon then pops. Well, we have one more thing to show you, Mark.
Uh-huh.
Oh, yeah. Oh, that's okay. Let's bring our shield up. Now I'm going to get this right here and show you that shield. And notice it looks just like a guillotine. So it's going to go right here on Mark's neck. And then we have right here a big cinder block, all right? We're going to put this right here on Mark's rock-hard abs. And then we're going to go ahead and use this, the sledgehammer. Yes, Mark, because I was in Mark's class and he didn't give me a good grade. And now it's time for payback.
We can talk about that.
Oh, not too late. Here's our experiment. Sledgehammer, brick, Mark, bed of nails. Does Mark live? Let's find out. Break the brick, and Mark is perfectly fine.
Yeah.
So you can see that, yes, more nails, less force, and the professor can live. But that's not quite the sometimes we end the show right with that demonstration, but we're going to give you one more demonstration. And for this, I got to move all these guys. All right? And here's what we're going to do. I got that up on the screen. We got ourselves a bath of liquid nitrogen. Right here. And, oh, thank you, Mark. And what I'm now going to do is I'm going to take some boiling water, which we have right there, and I'm going to drop it into liquid nitrogen. And now you can see liquid nitrogen, 77 Kelvin, or about minus 200 centigrade, or about minus 320. Boiling water, dramatically warmer, right? You see that temperature difference, almost 300 Kelvin. Well, what happens when you combine those two things in a sudden way? I say we find out. And by the way, this is the end of our show. Thank you so much for joining myself, Mark. If I can say, it's been a pleasure to work with him all these years. Oh, yes. I hope that next time we do this show, we have a room filled with people and all these problems are past us. Let's hope so. And thanks again to our great, great, great student workers. Fantastic job today. This is going to be fun, though. Mark, you hold on.
Yeah.
And right here. And now, how's that? Is that okay? Boiling water.
Do you have better gloves?
I put duct tape around.
Oh, duct tape. Okay.
And the end of our show was basically, we're going to disappear in a fog that we're going to create just by the dropping of this boiling water into the liquid nitrogen. We'll see you for the Faraday shows this December. And like I said, I hope we're all in this room. 3, 2, 1.